When we read about computer networks in the newspaper, it's often because they've been attacked or compromised. Almost every week we read about hackers breaking in and walking off with millions of credit card numbers and other private data, perhaps following a phishing attack or by exploiting some other vulnerability to access a supposedly private network. Or we might read about a new worm that is designed to take over computers, turning them into an army of botnets, such as the infamous Code Red and Slammer worms of the early 2000s. Botnets are armies of infected computers controlled by a master that are commonly used to send spam. While spam levels appear to be dropping slightly, reports suggest that between 75% and 95% of all emails sent every day are spam, adding up to hundreds of millions of emails per day. Worms are also sent by one government to another. For example, when the 2010 Stuxnet worm, which is widely believed to have been created by the US and Israeli governments, was used to attack centrifuges used for processing nuclear material in Iran. In this video, we're going to look at some ways that a network can be compromised by an attacker, and I'll explain the security characteristics we want from a network. Let's start by exploring the different ways a communication can be compromised. The first and simplest way is for an attacker to eavesdrop on someone else's private communication. This means passively sniffing and recording network data, or it could mean listening to the metadata, such as noting that a connection has been made without necessarily recording the data inside the connection. Connection metadata was made infamous recently when the NSA acknowledged recording information about calls and connections made without supposedly recording the contents. There are many ways to tap a network. For example, at the physical layer, an attacker might passively tap an electrical or optical cable. Or, as you've seen before, we can listen in to Wi-Fi because the packets are broadcast for everyone to hear. A third way is for an attacker to persuade a router to duplicate and forward copies of packets. In each case, the attacker can use standard tools such as Wireshark to decode the protocols and understand the user's data. A second type of compromise is when an attacker modifies, deletes, or inserts data as it passes through the network. In other words, they're actively tampering with our data, changing the contents of the packets, redirecting packets to a different rogue server without us knowing, or taking control over our end host. This might happen by persuading us to download malware based on a phishing attack, or by exploiting a vulnerability in our computer or the way that we communicate. For example, later we'll see how it's possible to hijack an ongoing TCP connection without either end knowing. Finally, an attacker might just want to prevent us from communicating at all. This kind of attack is usually called a denial of service attack. Sometimes these attacks are performed by swamping servers or entire networks by generating billions of messages from different botnets spread around the internet. We'll learn more about denial of service attacks in a later video. Let's take a look at an example of eavesdropping. Imagine that Alice is making a purchase online from an e-commerce site. She's using a laptop connected to her local Wi-Fi access point, then over the internet to Amazon.com. She browses the site and makes her credit card purchase using vanilla HTTP. Unfortunately, what she doesn't know is that the bad guy attacker is listening in to what she's doing. There are a few ways the attacker can eavesdrop. For example, by listening to or sniffing the Wi-Fi packets broadcast into the air. Anyone with a laptop and the Wireshark tool can listen to packets in the air and, if they're not encrypted, decode their contents. Alternatively, the attacker can eavesdrop on the physical wire by placing a passive detector to pick up small electromagnetic signals that leak from the cable. Or the attacker might insert an electrical connection onto the wire itself. If the attacker is eavesdropping on a long-haul link in the internet backbone, they're more likely to be tapping into an optical fiber. This can be done by placing a device called an optical coupler, which diverts a small fraction of the optical signal onto a second optical fiber, which can then be listened to and decoded. An attacker without physical access might manage to subvert the switches and routers along the path, tricking one of them into duplicating data and forwarding it to the attacker's computer. This can be done by remotely subverting Ethernet IP or DNS traffic. We'll see examples of all three later. Or the attacker might manage to break into the router console and take over the router completely. In our example, If the attacker successfully eavesdrop on the clear HTTP communication, he or she can learn Alice's private data, such as her credit card number and a home address. In a later video, we'll learn about how HTTPS prevents this from happening in practice. If the attacker is able to insert herself into the middle of the communications between Alice and Amazon.com, then the attacker can terminate the HTTP connection in the middle, pretending to be Amazon to Alice and pretending to be Alice to Amazon. The attacker could simply pass through the data, recording it without changing it. Or the attacker could alter the data, for example, to modify the shipping address, causing the purchased items to be delivered to the attacker instead of Alice. These so-called man-in-the-middle attacks are very hard to detect because both parties can think they're talking to a legitimate end host. A third line of attack is to redirect the traffic away from the server without Alice realizing that she's not actually talking to Amazon. If the attacker is able to fool the router to forward packets destined to Amazon.com to the attacker instead, then the attacker can respond and pretend to be Amazon. Or the attacker might fool Alice's DNS server into returning the attacker's IP address when Alice is trying to look up Amazon's IP address. In each case, Alice can be forced to browse the attacker's website and be encouraged to enter her credit card information there instead. Clearly, Alice is not happy and would like her communication to be more secure. In general, when we say we want secure communications over the internet, we're saying that we want secrecy and confidentiality. We don't want anyone to listen in to our communication. For this, we use encryption, and we'll describe how it works in one of the upcoming videos. We want integrity. We don't want our messages to be altered in transit. The most common way to prove that a message has not been tampered with is to attach what is called a message authentication code, or MAC. MACs are based on encryption as well, coupled with calculating a hash over the transmitted message. We'll study message authentication codes in an upcoming video. Third, we want authentication. We often want to confirm the identity of the other party we're communicating with. In our example, Alice wants to know that she is really talking to Amazon, who she trusts, before entering her credit card details. In a later video, we'll study digital signatures and certificates that help us ensure that we're really communicating with who we think we are. Finally, we want uninterrupted communication. We don't want someone to prevent us from communicating in the first place. You may have heard of denial of service attacks when an attacker floods a network or a set of servers to prevent them from working properly. We'll study denial of service attacks shortly. In the next few videos, we're going to study different types of attack. We'll study eavesdropping, redirecting Ethernet, IP, and DNS traffic, hijacking a running TCP connection, and denial of service attacks.